Good morning, everyone. This is Rebecca Bailey, and I will be your moderator for today's webinar. Before we start the webinar, I just wanted to give one short housekeeping item. You can ask questions for the presenter by entering the questions into your questions pane on the GoToWebinar side panel. You can enter the questions at any time during the webinar. Dr. Bies will be taking the questions at the end of the webinar. So our speaker today is Dr. Bies. He is currently a professor of pharmaceutical sciences at the School of Pharmacy and Pharmaceutical Sciences, as well as a member of the Institute for Artificial Intelligence and Data Science at the State University of New York at Buffalo. Prior to this, he was an associate professor of medicine and medical and molecular genetics at the Indiana University School of Medicine and director of the Disease and Therapeutic Response Modeling Program for the Indiana Clinical Translational Sciences Institute. He serves as a project scientist at the CAMH, University of Toronto, on the editorial boards of the Journal of Pharmaceutical Pharmacokinetics and Pharmacodynamics, Clinical Pharmacology and Therapeutics, the Pharmacometrics and Systems Pharmacology Journal, Journal of Clinical Pharmacology, Biopharmaceutics and Drug Disposition, and the British Journal of Clinical Pharmacology. Robert is a member of AAPS, FISoP, ACCP, and ASCPT. He's also a fellow of the International Society for Pharmacometrics. Robert received a bachelor's degree in pharmacy from the University of Toronto, a Pharm.D from UT Health Science Center in San Antonio, and the University of Texas at Austin, and a Ph.D. in pharmacology from Georgetown University. This was followed by postdoctoral training at the Center for Drug Development Sciences. His research focuses on the application of pharmacometric approaches in HIV, opiate addiction, pediatrics, psychiatry, oncology, and neurology, as well as novel methods development, including machine learning approaches to model selection and optimization methods for parameter optimization in dynamic systems. We are thrilled to have him today as the speaker, and so I'd like to give a very warm welcome to Dr. Robert Bies. Robert?
Thanks, Rebecca. Much appreciated. Thank you for the opportunity to present today. And so I'm going to be speaking about a sort of long arc of work that started over 20 years ago in collaboration primarily with Dr. Mark Sale, and is continuing with our efforts in the area of the implementation of some of these techniques in Python with a package called pyDarwin. So as we are well aware, there are many challenges to stepwise model selection in the area of nonlinear mixed effects modeling. Bear with me a minute. It appears the
Try clicking on your screen.
There it goes. Okay, sort of frozen for a moment there. So the local stepwise search or stepwise regression approach has some limitations in particular in the area of nonlinear mixed effects modeling. And you know, historically, one took a Bayes or covariate free model, kept known physiology in mind, maybe compared different compartment structures, lag time mixture models, etc. And then eventually came up with a final model that had a baseline structure, and then maybe evaluated covariates with single forward addition and then backward elimination strategies. And many years ago, in 1994, Janet Wade, Stuart Beal, and Nancy Samble published a paper on the interaction between structural, statistical, and covariate models in population PK analysis. And what this paper highlighted were the interactions amongst these different elements of the model, and that selection of one aspect of the model might affect the subsequent selections. And so this is sort of the this is one of the motivations in considering alternative model building approaches. So now, those of you who know the non-mem manuals and use non-mem regularly will recognize this schematic. This is a schematic illustrating sort of the classic model building approach, starting with a simple basic model, checking it runs, checking some basic output, and following this schematic sequentially to build a model. And this stepwise approach was largely considered for convenience because of computational times and other sort of logistical issues in the early days of nonlinear mixed effects modeling in the era of PK/PD. So one of the challenges is you can evaluate these models, but you very rapidly come up with a number of models that becomes more and more difficult to evaluate. So here's an example where you have one or two compartments. Maybe you have a lag time. You have a few covariate relationships. The continuous relationships might have 4 options, none, and 3 functional forms. Categorical covariates might have single options, and then whether or not there are hierarchies of variability on the different parameters. And in this case, we have almost 100,000 model candidates. Now, currently, given computational speeds, and if your model runs relatively quickly, maybe you can run an exhaustive search, but it's not generally a practical component. These numbers increase quite dramatically. So here's an example. Wait for it to come up. Here's an example illustrating the implementation of a tumor growth and response model that was applied to, and it's published in this citation here. And actually, that should be 2022. This is Mohammed Ismail et al. And you see that if we consider for structural model and killing models for a tumor trajectory and options with respect to the individual variability on different parameters in the model, and the error models, we have over 3 million possible combinations. So this rapidly becomes untenable. So perhaps a way to search that space of models a little more fully without doing an exhaustive search, perhaps and without the limitations of a stepwise search that would search a very, very small fraction of these, one might consider evolutionary algorithms. And genetic algorithms was one that Mark Sale had originated in the late 90s and early 2000s, applied to nonlinear mixed effects modeling. And so what are genetic algorithms? So it's a means of evaluating factors in a model where more than one factor can be changed in a single step. It's a way to partially automate the search to maybe allow a more complete evaluation of a full grid search or an exhaustive search for a particular candidate model. And so genetic algorithms, wait for this to come up, replicate the survival of the fittest. And I've got some of the John Holland references for some of the early articulations of this. And as an evolutionary process, it's imposed on the selection and survival of the best model descriptions. One calculates an indicator of how healthy a particular individual model is in the population. And it's utilized in multiple fields, for example, placing cell phone towers, predicting stock performance. General characteristics of genetic algorithms is that good characteristics in that model pool become more likely. And it's efficient at finding good regions of the solution space, even though it's somewhat of a brute force approach. It finds good regions of the space, but it doesn't necessarily find the best. So you can get into sort of the general vicinity of where an optimal, at least numerically optimal solution may exist. There's a few adaptations that were implemented, and these include elitism. So this is retaining the best candidate to the next generation, because it is possible in an evolutionary algorithm to lose the fittest member of the population, and so these are artificially carried forward to the next generation. And a local search hybrid, because this algorithm brings us to the region of a good region, and ideally the region that contains the best solution, but doesn't identify that best solution necessarily. A greedy search algorithm like the downhill search, local search hybrid, can compare candidates by changing the genome, by changing the model features, and we represent these as bits. I'll talk about that in a minute. By changing those bits one by one, and you can evaluate that every n generations. So here are a couple of citations for the early implementation with respect to PK/PD and disease progression modeling in the Journal of Pharmacokinetics and Pharmacodynamics. The potential models are reduced to a bit string, a base 2 number assembly that reflects the model's genetic code. So each model feature, the number of compartments, covariate relationships, for example, is coded as a base 2 number. So if there's only 2 options, the values are 0 or 1, it's a single bit. If there are more than 2 options, then you have to specify multiple bits to reflect that. These features are strung together to form a bit string, which is effectively the chromosome of the model. It's a series of genetic features. The model can be reproduced on the basis of the bit strings that result. So you have a bit string, and then you can translate that back to model features. So this is a figure that appeared in the British Journal of Clinical Pharmacology quite a few years ago, a paper by Sherer and Sale. You see that the genome of the model is highlighted at the top. And you have a gene, for example, for number of compartments, a gene for the effective weight on clearance, for age on clearance, etc. And then for the between subject variabilities. You select a feature, right? So gene 1, the number of compartments, the code is, let's say, 0, 1, so that's a 1 compartment model with first order absorption, right? A 1, 0 would be a 2 compartment model with first order absorption. The code is inserted into the model template. You see the token, and then you compile and run the resulting model. So more specifically, with respect to the substitution of these features, this table shows a model feature on the left-hand side, and the feature options, second from left column, the bit string code, and then what gets substituted into nomen. So if we go to, for example, the effective weight on clearance, it's the bottom left part here. No effect has a bit string code of 0, 0, and the nomen code that gets substituted is no text. It's basically a blank. If you have a linear effect here, then it adds this plus theta times weight, for example. And you'd specify also that it would add some initial estimate for your next theta. Power models 1, 0, 1, 1 would be exponential effect, etc. So the genetic algorithm approach that this represents, even though it's a composite function, we're calling it a single objective because it's a single fitness function that we are optimizing against. We initially used user-defined criteria. The defaults that were specified initially in that historical work were based on the -2 log likelihood. So that was the core of this fitness function, adding a default penalty per model variable of 10 points and a penalty for failure to converge of 400 points, covariance of 400 points, and correlation of 400 points. And those were chosen arbitrarily, right? Because we like models to converge. We'd like there to be a covariant step, and we'd like there to be a correlation, but these could be customized. And so we also explored some multi-objective approaches, and I'll talk about these towards the end of the presentation. But this generates a Pareto-fronted pairs of objectives. For example, -2 likelihood versus the number of parameters in a model. So this figure is illustrating the general schematic of the approach. So we create an initial random population of models. So you pick some number of models you'd like to that would represents this is the initial generation. And you run that population of models, maybe in non-mem, maybe in something else. You use non-mem to generate the -2 log likelihood and other indicators of fitness. And we calculate the fitness. Was that penalty, the set of penalties that that was shown earlier? We select parents from the population. In this case, it was proportional to the fitness. They were scaled, and then the likelihood of choosing them based on having a higher fitness and higher probability selection. Can incorporate crossover and mutation, and then you create a new and ideally better population of models, rerun, and continue this cycle. As you continue this cycle, as I mentioned earlier, you get to a region of space, of the solution space, that has good models, good solutions, but not necessarily the best numerically optimal solution. So this is where the hill climb comes into play. You take the best models in each niche from that run, and then we swapped out each bit one by one. So 1 bit downhill search. It changes the features per how we illustrated the implementation previously. Calculate the fitness and select models that are better than the base model. So you're basically doing exhaustive search of up to 6-bit changes that resulted in the better model in this early implementation. And this was set initially to run every 3 generations. Currently it's set for every 5, but you can customize that. So how did this approach do? So again, more examples on the implementation here of this original approach. We have pharmacokinetic data for 7 compounds. And the genetic algorithm search was set up to recapitulate identical model options and decisions that were undertaken by the modeler that was doing the stepwise modeling search, or had done already, because many of these were already published. Then we compared the information criteria of the final models and compared the model structures. So we still use that default fitness function, but then we compared information criteria to evaluate how they did. All right, so in terms of the general data that were available, the data for the 7 compounds, a mixture of intravenous and oral administration between about 70 and over 500 individuals, with just over 400 to over 1,500 samples available. And they were supplied by a variety of studies, with the majority coming from the clinical antipsychotic trials of intervention effectiveness trials. So here we see the model structure and the covariate options that were assessed. So for example, for the intravenous citalopram example here, we assessed only a 2-compartment model, didn't look at model structure, but evaluated 7 covariates. With one exception, FISoP with interaction was the estimation method used. Number of covariates ranged from 7 to 10, and typically either a single model structure was fixed, or a compartmental structure, I should say, or 2 were assessed. In the D-methyl-allgaldenomycin example, we also included the potential for inter-occasion variability. And for the risperidone, we included the possibility of a mixture distribution for clearance, given that this is a drug metabolized by CYP2D6, and we did not have genotype predicted phenotypes, so we was likely to have a multimodal distribution. And in the original stepwise model, a multimodal distribution on clearance was identified. So how did these do? Well, we had successful convergence for all of them, for both the stepwise approach and the genetic algorithm approach. However, for the data that arose from the CATIE studies, at least the models for olanzapine, pirfenidone, risperidone, and ziprasidone, required fixing the absorption process. These were sparse samples, and not a lot of samples were available in the early absorption phase. The single objective GA did not actually could actually estimate those parameters and converge. In terms of the covariance step, for the stepwise model, it was unsuccessful in 2 of the cases for IV citalopram and for pirfenidone. Keep in mind, we were using non-MEM5 for that time, and so perhaps that wouldn't be the case now. And then it was successful for all of the single objective GA candidates. Now, in brackets, what is shown here are the condition numbers, right? And so what you see is that we didn't include it in this early instantiation, the penalty for condition number. And so some of these models that successfully converged and had covariance steps, et cetera, had some pretty high condition numbers. Although, for example, with risperidone, when we added a penalty for the condition number, we ended up with a model that was very, very similar. It was a different residual unexplained variability model, same, basically very similar features otherwise, and a much smaller condition number. So how did these models compare in terms of the AKK information criteria? Well, for 4 of the 7 compounds, we had more than a 10-point improvement in with the genetic algorithm approach. Of course, there was more than, and we were using a 10-point penalty for 1 parameter, so it's not really the, the AIC is 2 points per parameter. So we went back and calculated the AIC. We saw this for the IV citalopram, the IV D-methyl allegaldenomycin, the oral olanzapine, and oral risperidone. And 3 of 7 had less than a 10-point change. These were the oral citalopram, pirfenidone, and the ziprasidone. They're all pretty close to each other. And so none were worse, at least in this set of 7. In terms of the structural models that were selected, 6 out of the 7 were in agreement with the stepwise. And 1 was different. The oral risperidone model, actually, instead of a 1-compartment model with a 3-component mixture on clearance, selected a 2-compartment model with a 2-component mixture on clearance. So let's transition now to pyDarwin. What was the impetus here? So there were some challenges with the coding of our single objective GA. One was that it was done originally sort of with an old version of Visual Basic that eventually we were not able to run any further and weren't able to update the code to new versions for Visual Studio. Dr. Mohammed Ismail, while in the lab, actually recoded the genetic algorithm, and actually he was really responsible for stimulating some of the interest in moving this forward, using an R-Shiny GUI in conjunction with PostFix non-mem and non-mem. Some of the challenges though with this recoded version, and you see the reference again at the bottom, and I apologize, it's not 2002, it's 2022. The initial step involved enumerating all of the possible candidates. And so as you get larger numbers of candidates, we started running out of memory. So we'd sample from those candidates to actually generate the model structures. In the paper, we also had an example of tumor growth, and that's the search space that I showed earlier, and with a PopPK model from a simulated data set. It did better with, it found a model that was quite a bit better numerically, at least for tumor growth, with a lower fitness function, several hundred points lower. But with the PopPK model, the GA approach actually came up with a model that was about 24 points worse, actually, than the stepwise. This code is available at the GitHub address provided here. Anybody who wants to try it, you may need to check versions in R of different sort of packages and that sort of thing, but it is something sort of fun to explore with the caveats that I expressed. Perhaps the biggest impetus was that there was an FDA HHS grant announcement, and this is the RFA that's listed here at the top of the slide. The development of a model selection method for population pharmacokinetics analysis by deep learning-based reinforcement learning. So, GA is essentially a brute force global optimization algorithm. And this grant announcement represented an opportunity maybe to explore other machine learning algorithms for model identification. The code for this, or at least the code if you do use the JSON files that we'll talk about in a few minutes, is posted at the GitHub site listed on the slide here, and as I said, is open for use. So pyDarwin, again, to recapitulate our principles with respect to the model selection. If you consider model selection, a search space is discrete. You start with a trivial model and search across that space. And in contrast to parameter estimation, where we have a continuous function, we start with an initial estimate. We make assumptions about the directionality of a solution or the relative probability of a solution, for example. And so that's pictured here in the top right panel. The discrete search space is shown in panel B at the bottom right. You have numbers of compartments and the elimination process, for example, illustrated here, and then the relative fitness function. It's illustrated. So for the traditional PK/PD model selection, a downhill method, we start from a base model and we add features. Doesn't consider necessarily the complex interactions between structural, covariate, and random effects. And it assumes that the optimal solution is continuously downhill from every other point in the search space. The machine learning model selection is to start from multiple random models, test the models, and have a better idea about the model structure, and update the information to the next generation to repeat this procedure. Now, with one exception, this is done with an explicitly discrete search space. The Gaussian process / Bayesian optimization actually attempts to do an approximation of the likelihood space across all the model candidates and has an uninformative prior that updates with actually the model solutions. So it sort of makes that discrete space pseudo-continuous or a continuous space. So what are the algorithms implemented in pyDarwin? Well, there's the genetic algorithm, Gaussian process / Bayesian optimization, a random forest algorithm, a random tree with gradient boosting, a particle swarm optimization, and also an exhaustive search option. So currently we're running one model search that has almost 1.7 million model candidates, just to see what that numerically optimal solution is in that entire space, so that we can compare them across all of these algorithms. I highlight 4 of the machine learning algorithms, as these are the ones that were applied in the example that I'm going to talk about in a few minutes. And these were implemented in Python with a combination of the DEAP, scikit-optimize, and PySwarms packages. So the genetic algorithm implementation in pyDarwin. Bear with me a moment while this appears. It seems it's a bit of a delay here. Okay. So again, we saw this figure before, but here we have our genome for the model. And for each of these genes, we've got the different elements representing different model components. So the workflow in this case is that we generate randomly initial candidates. We select the best parents, in this case now using tournament selection from the candidate pool. And in the candidate pool, we also apply mutation and crossover to create the next candidate pool. And I'll illustrate that in more detail in the next slide. And then we repeat that process until no further improvement is observed. Okay, so here we have the implementation of the illustration of the implementation of tournament selection and the crossover. So again, the bottom right, we see our genome representation of the model and the model features. We undertake a tournament selection. So a model is selected at random, and then a competitor model is selected. And depending on which model is more fit, that one is actually added to the parent pool. And then from the parent pool, there's a crossover that is done for pairs of parent models. And so the first thing is that we swap model information with the probability of crossing over, okay? And then we also use a random probability to select where in the genome that crossover is going to occur. So what is the position where the quote unquote binary bit string / genetic material is going to be sort of cut and exchanged. And so this is illustrated here in the top panel. You see that there's two triangles illustrating the cut points for the crossover, and then, excuse me, and then these materials are exchanged. So we go from a two-compartment model with no effective weight on clearance, a linear effective weight on volume, and an exponential effective age on clearance, and a exponential effective sex on clearance, a combined error model, and that switches with the other elements that were in model 343. So we now have an exponential effective weight on clearance, no effective weight on volume or age on clearance, a linear effective age on volume. And then this is repeated. And then there's also the probability of mutation. So you may get these progeny, but there may be a mutation. So mutation involves taking one of the bits and changing the bit from a 1 to a 0 or a 0 or a 1. So here we have the gene for number of compartments. We go from 0, 1, and that changes to 0. Just taking a second here. Oh, okay. To 0, 0. All right, let's do that. Yes. Okay, the Gaussian process. So these figures that are from the scikit optimize part. So the workflow is for the unknown objective function, we treat it as a random function. So there's a prior over the entire likely, objective function space, right? For all possible candidate models. So this is better to use with smaller scope of search where you have fewer models, although we have been able to get it to work with search spaces as high as a couple of tens of million possibilities. It does run very, very slowly. So first we treat that as a random function and place a prior over it. And after getting some observations, the prior is updated with a posterior distribution where the observations are, we create those random models. We actually calculate the objective functions or the fitness functions over that space, and then update the function to represent that space. And then we apply. Wait a second. It's just taking a second to show up here. All right, and so we have here is the true function. You can see in the red with the pink band, and the red dots are actual observations, and the green is the initial Gaussian function to approximate this. We apply an acquisition function to choose the next query point, sort of ask, okay, what if we try this? And then we calculate that point, and we update this, or the algorithm updates this component. Here we see the acquisition function, and this point is taking a minute to load. And again, we're getting closer and closer now to the approximation of a true function. You can see the acquisition function choosing the next point to assess. And again, getting a better and better approximation until we get a final recommendation. The random forest is implemented again with creating random models and then evaluating those random models as random or with a set of random trees, and then aggregating those trees for the features. And so here we have a model sample, and we run the record down each tree and do the averaging to get an average fitness value, and repeat that over multiple sort of generations, multiple iterations. And then you find a new query point based on this function, and after this, you make there's a recommendation based on the best estimate from the optimizer. And so typically, Gaussian, the random forest, for example, is a supervised learning process. These are all in the space of sort of unsupervised learning, in that we're evaluating a fitness function and we don't know what the best solution is. And so both the Gaussian process, the random forest, the gradient boosted tree represent some sort of flavor of reinforcement learning, in that it is searching, using these approaches to search across fitnesses that are not pre-specified in terms of an optimal fitness. So it's looking for the best that it can find. And as in the original assessment, a local downhole search is incorporated into all of these algorithms. And this is to ensure an efficient selection of the best possible models. And so this is illustrated here. You can see some screen caps here for what this looks like when you run this in pyDarwin. You can do a local 1-bit search and local 2-bit search every 5 generations. And again, you can customize the number of generations. And so for n bits in a system, local 1-bit search will need to run n models, because you're swapping each of those single bits. Okay. And for a local 2-bit search, you need to run n by n minus 1 over 2 models. So the number of models to assess as you increase the number of bits that you're sampling, in terms of the numbers that you're changing at the same time, will increase rather dramatically. So, for example, if we have a 16-bit search, that's 120, 16 models for the 1-bit search, 120 for the 2-bit search, 500 plus for the 3-bit search, and over 1,800 for the 4-bit search. So here is an example, and this is from a page poster that was presented last year. We have a simulation model with a linear 2-compartment model with first-order absorption. And this is a list of the typical values. We included 3 true covariates. Right, so or 3 parameters that have true covariates, including continuous and categorical covariates, and we added 3 additional quote-unquote covariates, basically just random numbers that did not have an influence in the model. We applied the Gaussian process, Bayesian optimization algorithm, the random forest, the gradient boosted random tree, the genetic algorithm, and the exhaustive search. The search space for the model selection comprised 10 dimensions. We had 3 compartmental model structures, whether or not volume was a function of weight, volume was a function of sex, whether or not clearance was a function of weight, clearance was a function of age. We had assumed between subject variability actually on most of the parameters in the model, but we searched on between subject variability on the absorption rate. And if we had a 2 or 3 compartment model, assessing whether or not the K23 or K32 parameters were a function of weight. Again, multiple absorption models, the between subject variability on the zero order absorption or lag time if it's present, and 3 different residual error models. So we had about 30 relatively limited search space of 13,000 candidate models. So the search criteria was based on the objective function value, plus a penalty for each parameter, theta, omega, and sigma of 10 points, plus 100-point penalties this time for failing to converge, for failing the covariance step, or for failing the correlation test, or for having a condition number greater than 1,000. So slightly different defaults, and you can customize You can customize the penalties, but these were the penalties that we used for this search. So in terms of the determination of the true optimal model from the exhaustive search, this is numerically optimal. This is not the model that we used to simulate. So it came up with a 2-compartment model, 0-order absorption, combined proportional additive residual error, and no covariates, and had a fitness function of 4818. So this is the exhaustive search. So running all of those 13,000 plus or minus models. Now, when we applied the simulation model, it had a higher or worse reward than the true optimal model based on the simulated data set. It failed the covariance step and it incurred a 300-point penalty. The fitness was 5118, so 100 points for each of the covariance, the correlation, and the condition number. So all of the machine learning methods failed to identify the true optimal model in terms of numerically optimal model. But they all identified the 2-compartment model, but without the 0-order infusion. So you might argue, well, look, that's the simulation model. That's actually closer to what you use to simulate this. But numerically, this was actually less optimal than the simulation model. And there's certainly points for discussion on that front. The 1-bit local search did not result in a true optimal model. We ended up with a fitness of 4922, which was the best 1-bit swap. A 2-bit search was implemented where all combinations of 2-bit changes were examined. So this was 120 models for 16 bits in this genome. And the best fitness then for all of the machine learning methods was then 4818. So it matched that the model that we identified with the exhaustive search. And there may be some examples that you come across that might need a 3-bit evaluation or a 4-bit, except that starts to get computationally costly. So to illustrate this, table here shows a upper triangular matrix, basically of objective function values. And so on the diagonal, you have the 1-bit changes. So here you have, for example, 5, you get a fitness function of 4918. Okay. And in any of the other cells, what you see are the effect of changing 2 different bits. So the best model was had the fitness value of 4818, and that involved changing bit 15 and bit 2 simultaneously in order to find that solution. So illustrating some of the performance of this implementation, how does one actually implement this? So there are 3 key files that have to be specified. These all have a JSON format. There's an option file, a token file, and a template file. The option file, which is kind of stuck here, specifies the algorithm, the penalty terms, the population size, and the number of generations, and among other things. You can call actually custom R or Python code if you want to calculate additional penalties. For example, a clinical significance penalty or penalty on predicting some particular aspect of the model output. All this is, there we go. Okay, so here you see algorithm is specified. In this case, it's the random forest, and we've gone too far. And we have penalties listed here. Now I'm going to go into more detail on this in subsequent slides. We have a token file. These are the features to test and the different options that you evaluate within each feature. And so the token file, which is, let me see if this will load. I see it's sort of freezing. Specifies what you're going to swap into the control stream. It specifies whether it's going to be blanks, what the functional forms are going to be, what the initial estimates will be for the features that you are actually searching over. And we get this to, and we'll stick to him. Okay, so this is, okay, well, this is the token file. So you can see that this has, for example, a token called KABMI. So it can either be blanks, or it can have these two functional forms where you've got a multiplicative power, so power function here, as well as an exponentiated form. And then you see here the initial estimates. And the third file, the template file, illustrates where these tokens are substituted. So you've got, you see here's our KA-BMI. So it shows up here and you get your first substitution from that token set. We're going to show this in a little more detail in a couple of slides. So you can specify just about any set of structures that you would like, even compartmental structures, even process structures. For example, as long as you ultimately provide swappable tokens that result in a syntactically correct model. So a runnable model, it may be unstable, it might give other errors, but you want at least to be, syntactically correct. So showing the options file in a little more detail here. So you specify the author. In this case, the algorithm specified as the exhaustive search. Batch size. Here are the penalties for the fitness function calculated. The path for non-mem, and this is also where you would add the path for any additional penalties. Let's say you wanted to predict a maximum concentration, or you wanted to evaluate the prediction of maximum concentration and include a penalty for not predicting that well. You could do that here. So that's some post-processing elements. Here's a template file. Again, you see that this looks like a control stream. It has a model structure here. Has swappable tokens, for example, V2 tilde gender 1, V2 tilde gender 2, under the dollar theta. So you can see where code bits would be swapped out. Right? It gives the general model structure. The tokens file, again, if you look here is V2 gender, we go blank, and we also have the exponential relationship here, which there's only two elements that are two groups that are specified here, each with two elements. These are substituted into the different tokens, and each token is named in sequence using this JSON format. So if we put the token file and the template file side by side, you see that here's our V2 gender 1 term on the left. Okay. And this can be substituted with the first element under the token V2 gender, which is just a blank, so there's no relationship. And the V2 gender 2, the second place where this appears in the control stream, substituted also with a blank because you have no relationship. These are the blue lines showing the different connections here. You can also substitute, we could alternatively be substituted for the exponential relationship. This is the red connectors. And you see for V2 gender 1, we have an exponential relationship between gender and the volume distribution. And then for V2 gender 2 token, we swap in the initial estimates and some comments about what this is, and that appears under the, that would be swapped out under the dollar theta block. So that's rather cumbersome code. So this is also implemented in Piranha. It's available from Certara, and I thank Certara for sharing the slides. And you can see that here you can actually, click from a GUI-based sort of interface, different model structures, covariate structures. You can implement your penalty structure. Now it's a little bit more limited, but it is more convenient for straightforward evaluations. Now, for the last few minutes here, I wanted to talk about something that's not implemented in pyDarwin, but is based on some older work, but I thought was just so interesting, and that's the multi-objective optimization idea, or multi-objective genetic algorithm optimization idea. So far, we've ended up with a single, quote-unquote, best solution. And maybe that's not, as helpful. There are a lot of solutions that are relatively close to each other. What may be more helpful is understanding what are the best choices given a particular trade-off. So what I'm showing here is a Pareto front. So, and you have on the x-axis, you have the cost of a vehicle. On the y-axis, you have the comfort level of that vehicle. And we have pictured here a Tata Nano at the bottom end here in terms of both cost and comfort. And at the upper end, we have the Rolls-Royce convertible in terms of both cost and comfort. Now, the upper part of this curve represents the non-dominated front, the non-dominated Pareto optimal front. So it represents, for any given cost, the most comfort that you can achieve. So it's where you want to be. You know, for this combination, you know, this is the best you can do. You don't really want to be in this, for example, this shaded blue area. So let's say you spend, it's whatever, $80,000, and your comfort is where in the middle of that blue space. Well, for that money, you could have had a much more comfortable vehicle. So cursor's disappearing here. A much more comfortable vehicle, or you could have spent less money and got an equally comfortable vehicle. It also allows you to choose again across that trade-off. What is important to the decision maker? What, instead of a single best option, what are the options that are the best solutions across a range of trade-offs, a range of features, of factors? So this was applied to that risperidone data set that we talked about before from Katie. What we see here are the number of parameters versus the -2 log likelihood. So number of parameters on the y-axis and -2 log likelihood on the x-axis. For 16 generations, you see a relatively stable front. So our Pareto front is this front that's moving, that's sort of on the bottom left and across. Okay. So how did we do? Well, this was the best stepwise solution. You can see that what we published was actually a dominated solution. We could have done better. For that number of parameters, we could have had a lower objective function, or we could we could have had fewer parameters. So how did the objective? We may want to be really along that edge to decide where we want to be. What are the non-dominated solutions? And so here we also, illustrate the best solution from our single objective GA, and this is of course with the original set of penalties, and it lies along that non-dominated front in this case. But it's only one of those solutions, and perhaps you'd like insight about solutions across those features, in this case, -2 log likelihood and the number of parameters. We also applied this to ziprasidone and perfenazine. So for ziprasidone, again, objective function value on the y-axis, the number of model parameters on the x-axis, and you can see that the non-dominated front is here along the bottom, and then it shifts up. But for the single objective GA, we seem to be on that front. For the stepwise, maybe a little bit off. Hard to know because there's a bit of a jump across those numbers of parameters and the objective function value. For the perfenazine example, we see the stepwise example is actually right on that non-dominated front, and actually the single objective GA is slightly off. Here we illustrate the same example with a data set for IV citalopram, intravenous citalopram. And again, we have the non-dominated front after 50 generations. The stepwise model is really quite a dominated solution. We could have done much, much better. The single objective solution lies right on that front. And again, you can look at the trade-off. So to conclude, these machine learning methods typically selected the better models versus stepwise selection, but not always. The one-bit downhill search is not always sufficient to discover the numerically optimal model. And maybe this MOGA approach, this multi-objective GA approach, provides insight into non-dominated solutions for specific metrics and trade-offs. I'd like to acknowledge many individuals. Mark Sale, now at Certara, who have been working together in this area for many, many years. James Craig, Keith Neforth, and Pavel Polosov, all at Certara. Eric Sherer, who is a fellow at Indiana University and worked on many of those earlier examples. At the University of Buffalo, Dr. Mohammed Ismail, who's at EPD, Xinong Li, who is now a PhD candidate in the lab, who worked on is working on the pyDarwin implementation. Siheng Yu, who worked on some of the examples for the R-Shiny example, along with Dr. Nikhil Pillai, and then of course our colleagues at the Food and Drug Administration, Yang Zhao, Feng Wang, Kalu Feng, and Meng Hu, and our grant support for the pyDarwin implementation from the FDA. And with that, I'll be happy to take questions. Thank you very much for your attention.
So we have time for just a few questions. One that came up and one that was on my list as well is from Eric, and he asks, how computationally difficult are these processes? How much faster are these methods compared to, say, an exhaustive search?
So they're typically much faster than the exhaustive search. So there's sort of two levels of comparison. There's having a modeler sit down and go through evaluating different model candidates. And at least in our first set of examples, that sometimes was weeks to a month or so for, say, a graduate student in the lab, or a couple of months, versus, let's say, a few days to a week to run a genetic algorithm. Our most complex models were typically completed on a 40-core server within a week to 10 days. That's across all of the algorithms, maybe in a search space of, let's say, 55 million possible solutions. So for a smaller search space where we had about 1.7 million solutions, the algorithms ran in a week or less. Okay, on that server, the exhaustive search for the 1.7 million example, we started 3.5 months ago on that 40-core server, and we are within now 25,000 models of finishing. So it's quite a bit longer. I hope that addresses the question. So the exhaustive search tends to take quite a bit longer than these machine learning searches. Of course, you can run an infinite number of generations or a big box, whatever you want to call them, and that would extend it. But typically, you get convergent. You don't see further improvement. We've typically seen 20 to 30 generations. You typically get stabilization.
So the next question is from Jen, and is there a limit for the dimensions for pyDarwin?
Probably the memory of the computer, right, for setting up arrays. So, like I said, we've done examples that are up to 55 million possibilities, but we have not done the exhaustive search for the 55 million possibilities because even if we put, say that we have maybe 200 cores we could dedicate to something like that, it would take 10 years to run the exhaustive search. But maybe I don't know if Mark is online, but really there's not a preset sort of limit. There'll be memory issues. So with the R-Shiny implementation, because we had enumerated the full grid, just listed features of the models. Once we hit about 50 million models, we would run out of memory on the server. And that's just making a list. So that's probably just a practical limit, but we don't have a explicitly preset limit.
The next question is from someone, I'm not going to be able to pronounce the name, but they ask, in a genetic algorithm-based approach, the algorithm may add random effects which may not result in little improvement, but it may not be necessary in a practical scenario. How do we prune out these models where the random mixed effect addition is also decided optimally?
So there's a couple of ways you could approach that. Well, how it was done initially was that, okay, does it improve our objective function value enough that a 10-point penalty for adding it, okay, is overcome? The second approach would be to say, well, let's say we put in a between subject variability, and you could put a penalty for the additional parameter, but you could also say that I think that between subject variability should be at least X% or result in a range of values of a particular parameter between X and Y. You could write a custom penalty for that and use that as a decision criteria. But as it's implemented right now in the default, it's just a penalty for the number of parameters. And of course, if you have too many random effects and you can't get the covariance step to run, or creates problems for other elements of the model, condition number and other things, then it sort of indirectly will contribute to being deselected in the model.
So we do have a note from Mark that says the memory footprint for pyDarwin is pretty small. The larger memory need is for multiple non-man runs in parallel. We are out of time. We do have a number of questions that have not been addressed. I'm going to send those on to our speaker, Robert, and let him communicate the answers with them. I believe that there are some people who will actually want to communicate this with you.
Right, I'm looking forward to answering the rest of the questions, and thank you again for this terrific opportunity to talk about the work.
Thank you so much. This has been very interesting, and I hope to see all of you at a future webinar. Have a great day, everyone.
Thank you. Bye.
Bye.
Okay, did you want me to stay on for a minute, or?
No, I'll send you everything.
Wonderful. Great.